Greetings to everyone. I am Ms. Rhea Fernandes, working as a lecturer in Department of Food, Nutrition and Dietetics from Milagros Degree College, Mangalore. So today I am going to deal with the topic carboxylic acid. So first of all, students, what is carboxylic acid? So carboxylic acid is derived from carbonyl group and hydroxyl group, the two functional groups. So this carbonyl and hydroxyl group together make up the main group, that is carboxylic acid group. So we move on to the synthesis of carboxylic acid, that is preparation of carboxylic acid. So these are the preparation. So the first method is oxidation of primary alcohols or aldehydes. In the oxidation of primary alcohols or aldehydes, the oxidizing agents such as potassium dichromate, that is K2Cr2O7 and H2SO4 is used. Here we have alcohols which on oxidation gets converted into an aldehyde and further it gets converted to an acid. So here we saw that there is a usage of primary alcohols and not secondary, because if we use secondary alcohols, it will get converted into a ketone and there will be no reaction further, since ketone won't get converted to an acid. But the primary alcohols will get converted to an aldehyde as shown here, and then the aldehyde on further oxidation will get converted into an acid. So these are the general reaction in which the R group, that is, it can be an alkyl or an aryl group, and then these are the examples where the R group is replaced by CH3 and CH2. So you can see that the ethyl alcohol is get converted into an ethanaldehyde and further it gets converted to an ethanoic acid. Next preparation, that is synthesis from nitrile. So nitrile is a C triple bond N group. So these nitriles are first generated from the alkyl halides, in which there is a removal of the sodium and halide group, and the halide group is replaced by the sodium, and hence we get alkyl nitriles, in which there is addition of water molecule and you get a molecule which is an intermediate formed, and this intermediate will get tautomerized, and then after tautomerization you get an amide, which on addition of water molecule you get the acid, in which the byproduct will be your ammonia group, that is NH3. Now in this reaction we see that the nitriles are getting converted into an acid, that is carboxylic acid. So this is the reaction, the general reaction in which the R group is used. This R group is an alkyl or an aryl group. So these are the examples where the R group is replaced by CH3 and CH2, that is ethyl chloride, which is get converted into an ethyl nitrile, which is the C triple bond N group, you can see. Then there is addition of water, which forms an intermediate, and then there is the amide group which is formed, which on acid, that is addition of dilute hydrochloric acid and water, you get the monocarboxylic acid, that is your ethanoic acid. The byproduct will be ammonia. Next, synthesis by hydrolysis of ester. Now students, what is hydrolysis? Hydrolysis is breaking of water molecule. Now in this reaction you can see there is ester used. This ester on basic hydrolysis, that is addition of sodium hydroxide in the presence of heat, like there will be a base used, that is sodium hydroxide, plus in addition to it there will be heating which is required in this reaction. Then further you will get sodium salt of the ester, that is RC double bond O ONA, which is called a salt, and the byproduct will be alcohol. Okay, it is ethyl alcohol since there is C2H5OH. Now this salt, sodium salt of ester, will further addition of acid, that is hydrochloric acid, will undergo acid hydrolysis and you will get your acid, that is monocarboxylic acid, and the byproduct will be salt, that is NaCl. So this is just a general reaction in which the R group can be replaced by aryl or alkyl group. So here is the example where we have used the CH3 in place of R, that is your alkyl group. So this is the example in which NaOH on heating you get sodium salt of the ester, Then further the byproduct is ethanol. Then this salt on addition of acid, that is acid hydrolysis, we get the carboxylic acid. Next, we move on to reaction of Grignard reagent with carbon dioxide. Now first we need to synthesize the Grignard reagent and to know what is the Grignard reagent. So here we can see the Rx group, that is an alkyl or an aryl group. As I previously said, the R group is an alkyl or an aryl group. This X is a halide. So the alkyl or aryl halide, with the help of a metal, magnesium, in the presence of dry ether, will get to form RMgX, which is called the Grignard reagent. So this RMgX is a Grignard reagent. Now this Grignard reagent will consist of some charges. That is, as we know, metal always consists of positive charge and the halide is a negative charge. And the alkyl group here is again a negative charge. So negative, positive and negative. And as it is written, it is reacting with the carbon dioxide. So carbon dioxide consists of CO and O, that is CO2. Now this carbon is a positive charged, oxygen is a negative charge. Now this negative charge and negative charge will go towards the positive charge and the positive charge will go towards the negative charge. So there will be reaction wherein the negative charge will get attached to the positive charge, that is your carbon, and the negative charge and the positive charge will move on to the oxygen atom. So you can see there the negative and positive together, the positive and the negative together. So here this reaction will lead to further hydrolysis, that is addition of H3O and also the breakdown of water molecule, which will further lead to the acid. So this is the third reaction in which the carboxylic acid is formed with the help of the Grignard reagent in presence of carbon dioxide. So here we saw the general reaction in which the R group is explained with the halide group, that is X. Now X can be chlorine, bromine or iodine. Okay, so in example, I have taken X as a bromine. You can see the Br group in which the ethyl magnesium bromide is converted to propanoic acid. So you can see there are 2 carbons and 1 carbon from the carbon dioxide. So in total the 3 carbons is come as a product. So if we want the propanoic acid to be formed, then the reactant should contain ethyl magnesium bromide along with carbon dioxide as a Grignard reagent reaction. Next we move on to carboxylation of alkenes. Now in this reaction, the alkenes in the presence of carbon monoxide and water with the help of phosphoric acid, that is H3PO4, under 400 degrees Celsius temperature, you get your acid. Now this reaction, you can see the general reaction in which only alkenes are preferred for this carboxylation. Carboxylation, the term only tells us that there is a usage of carbon monoxide and not carbon dioxide. So you can see there is only 1 carbon and 1 oxygen molecule reacting with the alkene. This is the example, general reaction, and this is the example in which you have the alkene, that is the ethene, is get converted to a propanoic acid, and the second example in which we have the propene, which is getting converted into a butanoic acid. So this is an isobutanoic acid in which there are 4 carbons, and in reactant you have only 3 carbons. So again we see here that the 2 carbon compound is getting converted to a 3 carbon compound, and a 3 carbon compound is getting converted to a 4 carbon compound. So here we see in this reaction also that the extra carbon atom which was not present in the reactant is taken from the carbon monoxide. That is the reaction in which we are using the component or a reagent, that is carbon monoxide. Last synthesis we move on to is synthesis from Melonic Ester. Now this is the Melonic Ester in which you can see the C double bond O, C2H5 is there twice in a molecule. So here also what happens, the alkyl or aryl halide in presence of melonic ester reacts in which the sodium and halide group is eliminated first in the first step, and in the second step there is addition of 2 molecules of water in which there is also removal of 2 ethanol molecules, and then we get 2 acid molecules. And since we know that at the start we were mostly preferring in the preparation only of monocarboxylic acid, and this, when we are doing the reaction, you can see there are 2 carboxylic acid formed, so it is giving rise to dicarboxylic acid. So to eliminate the 1 carbonyl group, we just remove the carbon dioxide group from this molecule, and the remaining, the product will be your monocarboxylic acid. So in this reaction we saw how the alkyl halide in presence of a malonic ester further undergoes the elimination of sodium halide group, and then there is a formation of a molecule in which there is addition of 2 molecules of water, from which the ethanol group is eliminated, and then again we get the 2 carboxylic acid group. From there again we are eliminating the carbon dioxide group, and hence finally we reach to our monocarboxylic acid. So this is just a general reaction in which the R group can be replaced by an alkyl or an aryl group. So next we see the examples in which I have used the bromobenzene, which is getting converted into phenylacetic acid. So you can see, students, that bromobenzene on reacting with malonic ester, the removal of NABR takes place first. Then you see there is an addition of water molecule here in the presence of heat, and then there is a formation of a molecule in which there is a removal of carbon dioxide again, and then we are getting a product that is your phenylacetic acid. So if we want to prepare phenylacetic acid from bromobenzene, we can prefer this reaction, that is synthesis from malonic ester. Another reaction which involves the use of aliphatic compound, that is from ethyl bromide, also we can prepare the molecule, that is butanoic acid. We can see that in this reaction too the same procedure is carried, in which there is removal of sodium bromide, and then we add water molecule in the presence of heat, and we get the compound from which there is a removal of carbon dioxide, and you get your product, that is butanoic acid. Next topic we move on to, that is dicarboxylic acid. Now first we should know what a dicarboxylic acid. The compounds which contain 2 molecules of carbonyl group and hydroxyl group, that is the 2 molecules of carboxyl compound containing in a molecule, that is called as dicarboxylic acid. So you can see that there are 2 C double bond OH, C double bond OH. So this molecule will be called as dicarboxylic acid, in which the N group can be 1, 2, 3 or even 0. So these are some examples of dicarboxylic acid in which there is just addition of CH2 in terms of N is equal to 0, 1, 2, 3, and then we get our molecules such as oxalic acid, malonic acid, succinic, glutaric, adipic, pymalic, subearic, azelaic, and the last is sebacic, and so on. So these are the examples of some dicarboxylic acid in which you have simple 2COOH group, that is 2 carboxylic acid group. In between there may be a CH2 group or there can be no CH2 group, but this will be in a successive flow, that is ethanoic, propanoic, butanoic, pentanoic, hexanoic, heptanoic, and so on. Next, we will study about its physical and chemical properties for your dicarboxylic acid. So we see in physical properties, the dicarboxylic acids are crystalline. So when we see the compound, it will be appearing to us as a crystals. The second property will be the melting point will be higher than your monocarboxylic acid. Dicarboxylic acid contains 2 carbonyl groups and 2 hydroxyl groups. So in comparison with your monocarboxylic acid, the dicarboxylic acid will be having higher melting point. The third one, we see that they will dissolve readily in water, but the solubility falls as the molecular weight increases. As you know, we saw in the previous slide that the carboxylic acid, as the CH2 group goes on increasing, there is increase in the molecular weight of the molecule, and hence it will not get so readily dissolved in water due to its high molecular weight. The oxalic acid, that is the first one, will be easily getting soluble in water, forming hydrogen bonds with water. But as the molecular weight increases due to successive addition of the CH2 group, the decrease in the solubility, there will be decrease in the solubility, and slowly this will go on. Moving on to last physical property, that is the melting point of dicarboxylic acid. We see in this, there will be the even number of acid will always have higher than the odd number, as if it's given the oxalic acid. If we see in the previous slide, oxalic acid contains 2 carbon atoms, melonic 3 and succinic 4. So 2 and 4 is an even number, and the melonic glutaric, the alternative compounds, consist of odd number. So if you see in the range of the melting points, the even number, that is oxalic acid, succinic acid, adipic acid, will have a higher range of melting point than the odd number of molecule. That is, if you compare, 187 will be higher than 135. Again, 185 is higher than 97.5. So here we see that 187 is the even number of containing carbon atom. The molecule contains even number of carbon atoms in oxalic acid, and in malonic acid there is odd number of carbon atoms. You see there are 2 carbon atoms, here there are 3 carbon atoms. Again there are 4 carbon atoms, here we have 5 carbon atoms. So the molecule containing even number will have a higher melting point, and the molecule containing odd number of carbon atoms will have a lower melting point. So this is a range in which you can compare the melting points of dicarboxylic acids. Now we move on to chemical properties. Now in chemical properties of dicarboxylic acid, the first, when we compare with monocarboxylic acid, the chemical property remains the same in terms of reaction. In dicarboxylic acid, they give mono or di derivatives to form salts, acids, amides and esters. And the third property, that is third property of chemical acid in dicarboxylic acid, is the lower members, that is oxalic acid, palmitic acid. These dicarboxylic acids have mutual interaction, and hence they don't react with other molecules fast, since they have a mutual interaction. Next is hydroxy acid. Now hydroxy acid is a compound in which the carboxylic acid will have a OH group attached to it. You can see the carboxylic acid is having OH group, that is hydroxy acids. So here are some examples in which there is hydroxyacetic acid, you have bromoacetic acid and the aminoacetic acid. So there are many types, that is the OH group, then there can be a Br, that is a halide group, then there can be an NH2, that is an amine group. Our main focus is on hydroxy acid, the compounds containing the OH group. Now these compounds are named from the compound which is containing the functional group, that is COOH. Now here you can see the COOH group, that is carboxylic acid group. Then we have 1, 2, 3, 4 and 5 carbon atoms. Total there are 6 carbon atoms as it is shown. So the numbering will start from the compound containing the carboxylic acid group, that is the carbon which is having COOH will be numbered as 1, then we move on like 2, 3, 4, 5 and 6. And in Greek letter also will be in the same order, that is alpha, beta, gamma, delta and eta. So here you see that the naming will be carried from the main carboxylic acid group, and then it will move on to the next carbon as 2, 3, 4, 5, and the naming in Greek letter will be also the same, that is alpha, beta, gamma, delta and eta. Now here you see that the OH group is attached to carbon next to the functional group carbon, that is next to the COH group. So as we learned previously, it is called as alpha hydroxy acid because this OH group is attached to the alpha carbon atom. So it will be named as alpha hydroxy propanoic acid. Propanoic because it consists of 3 carbon atoms, 1, 2, 3, and the hydroxyl group is at the second carbon atom, which is named as alpha carbon. Hence the name goes as alpha hydroxy propanoic acid, or there is another way to name it, that is 2 hydroxy propanoic acid, since the OH group is at the second position. So it can be named in 2 ways, that is 2 hydroxy propanoic acid, or it can be also named as alpha hydroxy propanoic acid. Next, you can see here that is used for halides, but as I told, we are focusing only on hydroxy acid, so this is of a major interest. Next, you can see many more examples such as hydroxyacetic acid. So here this is a simple acetic acid, that is CH2COOH. The hydroxyl group is attached to it, and hence it is named as hydroxyacetic acid. The common name is glycolic acid. Next is alpha hydroxypropanoic acid, as we have seen in the previous slide. Then you have certain other examples, that is malic, tartaric, and citric acid. So you can see that the OH group is attached on every molecule, 1, 2, 3. Okay. So these are the examples of hydroxy carboxylic acid. Last, we learn about their physical and chemical properties of your hydroxy acids. These are the physical properties in which we have hydroxy acids also to be appearing crystalline. They are liquid molecules like your syrups. Then we have the melting and boiling points, which are higher as compared to dicarboxylic and monocarboxylic acids. The third one is they are more soluble in water, because we see that in hydroxycarboxylic acid there is a OH group. Due to the presence of the OH group, it forms intermolecular hydrogen bonding with the molecules of water, that is H2O, and this leads to the more solubility of water with the acid. The last point, that is these hydroxy acids are more stronger than the other acids due to presence of electron withdrawing OH group in the molecule. So these are the physical properties, and next we move on to chemical properties. So chemical properties, you can see that the hydroxy acids have a carbonyl group and a hydroxyl group in the same molecule, and they are similar to the monocarboxylic acid and dicarboxylic acid. The major interest of the chemical property for your hydroxy acid is it will be having a interesting reaction in hydroxy acid with the effect of heat. When there is an application of heat on the molecule, or there will be any external reagents reacting to it, there will be some different chemical properties which will show reactions different from your monocarboxylic acid and dicarboxylic